Today, Internet of Things is everywhere, from smart buildings which have automated ventilation and air conditioning to smart grids, turbines, windmills, microgrids, and even nanogrids. It is also in the transportation, industrial automation, healthcare, supply chain, and even in the IT industries. The Internet of Things is changing everything, but unfortunately, many industries and consumers are discovering themselves at the verge of a security nightmare. The drive to make all devices smart is creating a frenzy of opportunities for cyber criminals and security researchers alike. These threats will only grow in their potential impact on the economy, corporations, business transactions, individual privacy and safety. Thus, securing IoT platform has become very important, and which is the topic of this video. Hello and welcome to our channel SecureNet. I'm Ravi and today we talk about Internet of Things, different attack types on IoT and some of the countermeasures which can help secure IoT devices or systems. IoT is when we have our electronic, electrical or electromechanical devices connect to the internet and talk to each other. These smart devices primarily revolve around three things. Sensors. These are components that sense something about their environment. There are sensors available for almost everything and they can be classified into different categories. Some examples are distance sensors, temperature sensors, and infrared sensors. Actuators. These are components that do something like lock doors, beep, turn lights on, or turn the TV on. There are different kinds of actuators, for example, hydraulic, electric, or thermal. Networking. These IoT devices talk to one another or to servers located in the local network or on the internet. Being on the network allows the device the common ability to consume and produce data. There are, of course, more components in an Internet of Things system, for example, storage, processing unit, a cloud, but at the basic level, any solution in the IoT space is either sensing something or actuating something. The best way to learn about the security of these devices is looking at what has happened in the past. By learning about the security mistakes other product developers have made in the past, we can gain an understanding of what kind of security issues to expect in the product we are assessing. The first product we will look at is Nest Thermostat. A smart Nest Thermostat is from a company or brand which is owned by Google. And one of the researchers mentioned some of the security shortcomings of the Google Nest that allowed the installation of a new malicious firmware on the device. This was done by pressing the button on the Nest for about 10 seconds to trigger the global reset. And then the device could be made to look for a USB media for the firmware upgrade by communicating with the boot pin. On the USB device, then a malicious firmware was present, which the device then used while booting. Another researcher, Jason, identified another vulnerability in the Nest products that involved sending a custom crafted value in the Wi Fi SSID details via Bluetooth to the target device, which would then crash the device and ultimately reboot it. This would also allow a burglar to break into the house during the duration of the device reboot of around 90 seconds, and that is without being caught by the Nest security camera. Philips home devices suffered from a number of security issues across the product range. These include the popular Philips Hue worm built as a proof of concept by security researchers Eel. In the POC, he demonstrated how the hard-coded symmetric encryption keys used by Philips devices could be exploited to gain control over the target devices over Zigbee protocol. It also included automatic infection of Philips Hue bulbs placed near to each other. In 2013, another researcher came up with a novel technique to cause permanent blackouts by using a replay attack technique to gain control of the Philips Hue devices. He discovered this vulnerability after he realized that the Philips Hue smart devices were only considering the MD5 of MAC address as a single parameter to validate the authenticity of a message. Because the attacker can very easily learn the MAC address of the legitimate host, he can craft a malicious packet indicating that it came from the genuine host and with the data packets with the command to turn the bulb off. Doing this continuously would allow the attacker to cause a permanent blackout with the user having no other option than to replace the light bulb. Philips Hue and many other smart devices today uses a technology called Zigbee to exchange data between the devices while keeping the resource consumption to a minimum. The same attack that was possible on the devices using Wi-Fi packets would also be applicable using Zigbee protocol. In the case of Zigbee, all an attacker would need to do is simply capture the Zigbee packets for a legitimate request and simply replay it to perform the same action at a later point in time and take over the device. The next device we'll look at is Imperial Dabman IoT radios. These radios had a weak password vulnerability that could allow a remote attacker to achieve root access to this gadget's embedded Linux BusyBox operating system, gaining control over the device. Attackers can then deliver malware, add a compromised radio to a botnet, send custom audio streams to the device, listen to all station messages, as well as uncover the Wi-Fi password for any network the radio is connected to. During testing, security researchers took only 10 minutes to compromise the password. Next, we'll look at LIFX smart bulb. Security researchers discovered serious security vulnerabilities in LIFX smart bulb, making it possible for attackers to inject malicious packets into the network, obtain decrypted Wi-Fi credentials, and take over the smart light bulbs without any authentication. However, most of the sensitive data exchange happening over the network was encrypted, which made the product look like very secure. But the researcher could figure out the AES encryption key, initialization vector, and the block mode used for encryption. And because this information would have been same for all the LIFX smart bulbs, the attacker could take control of any light bulb and break into Wi-Fi. Next, we look at some of the IoT attack types. The first one, and very common, is HVAC exploit. HVAC or heating, ventilation, and air conditioning systems are present in almost all companies. HVAC systems have many security vulnerabilities that are exploited by attackers to steal login credentials, gain access to HVAC system, and perform further attack on the organization's network. HVAC systems are generally connected to the networks of various industries, government sectors, hospitals. These systems provide remote access rights to HVAC vendors and third parties to support remote administration of the system, such as remotely monitoring energy consumption and temperatures at various places. In addition, many HVAC companies provide common login name and password to different organizations. Attackers take advantage of these and obtain remote access to corporate networks and steal confidential information. Usually, the steps are as follows. Attackers uses any search engine like Shodan and searches for vulnerable industrial control system. Based on the vulnerable ICS system found, the attacker then tries for the default user credentials again using some online tools. If default credentials are not changed and attacker is successful in gaining access to the ICS system, then attacker tries to get access to the HVAC system remotely through ICS system. After gaining access to the HVAC system, an attacker can control the temperature from HVAC or to carry out more attacks in the local company network. Next, look at jam and replay attack. Most of the smart vehicles today use smart locking systems, which uses radio frequency signals transmitted in a form of code. The code is sent to the vehicle is always unique and it is used only once. The attacker can capture this code and they can use it later to unlock the garage or the vehicle. This code is performed using a jamming device that both jams the signal and sniffs the code. Usually, the steps are as below. Victim presses the car remote button and tries to unlock the car, but attacker uses a jammer that jams the car's reception of rolling code sent by the victim and simultaneously sniffs the first code. Car does not unlock. Victim tries again by sending the second code. Attacker sniffs the second code as well. On the second attempt by the victim, the attacker forwards the first code that unlocks the car. The recorded second code is used later point of time by the attacker to unlock and steal the vehicle. Attackers usually make use of tools such as RFCat, RFCrack to perform this kind of attack. Next, we look at a smart grid attack. In this, attackers gather basic information about the target organization using various social engineering techniques. After that, he sends phishing emails to the employees, thousands of employees, with a malicious attachment. When the employee opens the email and clicks on the attachment, a backdoor is automatically installed in the target system. Using the backdoor, the attacker gains access to the private network of the organization. After gaining access, he can access the SCADA systems that controls the grid. Then attacker can replace the legitimate firmware in the devices with malicious firmware, or the attacker can disable the power supply of any particular place by sending malicious command to the substation control systems from SCADA. Let's see some more types of attacks. Civil attack is on vehicular ad hoc networks where an attacker uses multiple forged identities to create a strong illusion of traffic congestion. Man in the middle attack is when an attacker pretends to be a legitimate sender and intercepts all the traffic. Replay attack, as names suggest, record and play. Attackers sniffs messages which may contain hashed passwords and then replay the same messages to gain the device access. Blueborn attack, Bluetooth and airborne, called blueborn attack. There are many Bluetooth vulnerabilities exploited using this. For example, blueborn flaw in the implementation of LEAP, low energy audio protocol. A large audio command can be sent to a targeted device and lead to a heap overflow with attacker controlled data. Since the audio commands sent via LEAP are not properly validated, an attacker can use this overflow to gain full control of the device through the relatively high privileges of the Bluetooth stack in the iOS. Device forging. If attackers get physical access to the device, then they can replace authentic IoT device with a malicious device. Forged devices then used to gain the access to the network. Side channel attack. In this, attackers gain information about side channels like power consumption or electromagnetic leaks. Basically, they try to guess encryption keys by observing the emission of the signals. In ransomware attacks, malware encrypts all the data of the device and then asks user to pay some money, which is usually in the form of Bitcoin, to decrypt the data. We all know about the most famous ransomware called WannaCry. In DDoS attack, attackers usually use thousands of compromised IoT devices to attack on a single server so that server is overwhelmed by the requests and it is no more accessible. These this is not an exhaustive list of attacks. There are many more types of attacks that affects Internet of Things. Let's discuss some of the countermeasures which are required for securing IoT devices. OWASP provides a very nice list of security issues, and let's take this list, which is called OWASP Top 10, as a reference for discussing these security countermeasures. The first point we have is insecure web interface. The web interface of IoT devices, or I should say IoT systems, should be tested against known vulnerabilities. Secure coding practices must be followed during the development of the web interface. Website should also implement several measures like prevention of use of weak passwords or account lockout mechanism in case of failed login attempts. The website should also be tested against cross-site scripting and SQL injection. HTTPS should be used instead of normal HTTP. This provides encrypted communication. The website should also utilize encrypted transport protocols and it should validate certificates. Next point is insufficient authentication or authorization. In an IoT system, there shall be proper authentication and there should be a way to implement multi-factor authentication if it is possible. The authentication should also provide mechanism like requirement of strong passwords and password recovery should be through in a secure manner. There should be a proper password expiration after a specific period, and also the application should include the option to change the default username and password. There shall be also proper authorization. Not everyone should get admin access by default, and the user should get the function access based on their credentials. It is also important to pay sufficient attention to network services. We must make sure that applications don't respond poorly to buffer overflow, fuzzing, or denial of service attacks. We shall also utilize tested, proven networking stacks and interfaces that handle exceptions gracefully. We shall avoid exposing unauthenticated protocols such as TFTP or unencrypted channels such as Telnet. Before deployment, it is very necessary that we turn off all the unnecessary services and the application must have some capability to react to an attack with measures such as lockouts or temporary firewall rules. Lack of transport encryption. It is very necessary that during the communication, the data is encrypted. The communication can be between device to device, or device to server, or device to the internet. We shall always take encrypted protocols, and if protocol encryption is not possible, then the data should be encrypted before transfer. And for the encryption, only standard algorithm should be taken. Privacy concern is one of the most important security issue with IoT devices because data can be aggregated and it may present unintended privacy concerns. So as a rule, we shall collect the minimum amount of data which is required. Also, the collected data should be properly protected using encryption at rest and also in the transit. Legal and compliance teams should be consulted to determine risk of data collection and storage. Also, data must be de-identified or anonymized. Next is insecure cloud interface and mobile interface. They are very similar to what we discussed about the web interface. For example, we shall make sure that weak passwords are not used. There shall be lockout mechanism, multi-factor authentication, testing for SQL injection and cross-site scripting. In case of cloud interface, all the APIs should be tested for vulnerabilities. In case of mobile interface, we must make sure that minimum amount of personal data is collected. There are several measures we should make sure for security configuration. For example, we shall enable 20 character passwords or user shall enable two-factor authentication. There shall be encryption options and also there should be proper logs created for all the security events. We must ensure that all applications are written to produce alerts and notification to the user for security events. The application should be designed in a manner that they have self-defending capabilities and a reaction plan. And all the design should be in a manner that they are evolutionary. So improvements can be added to a system or device in the future releases or updates in secure software or firmware. Here we must ensure two things. First is application should have a proper capability to update, and secondly the update should be delivered in a secure manner. So all devices and applications should be written to include update capability and can be updated as quickly as possible when vulnerabilities are discovered. Devices should always validate cryptographic certificates and discard updates that are not properly delivered or not signed. We shall provide a mechanism for issuing, updating, and revoking cryptographic keys as well. Key management and life cycle should be taken into consideration prior to the deployment. This includes the SSL trust store or root trust on a device. We shall plan for having IoT edge devices fall into malicious hands. We shall utilize wherever physical security protections are available, disable any testing or debugging interfaces, utilize hardware security modules, cryptographic coprocessor, and trusted platform modules wherever possible. We shall consider the implications of a compromised device. We shall not share credentials, application, or cryptographic keys across multiple devices to limit the scope of damage due to a physical compromise. We shall also plan for the transfer of ownership of devices and ensure that data is not transferable along with the ownership. Also, applications should be written to utilize a minimum number of physical external ports on the device. The application should also allow for disabling of unused physical ports such as USB port.